Okay, so let us talk about electroosmosis. Before we talk about electroosmosis, let us talk about the electrical double layer, the Debye layer, which is an important concept in electroosmosis. So if you look at here, we have a surface which has negative charge, okay, and over the surface we have a liquid present, an ionic liquid. Because of the negative charge on the surface, the positive charges are attracted towards the wall, and at the very interface on the wall these positive charges are strictly bound onto the negative charges, and these positive charges are immobile, okay. So they form an immobile layer which is known as Stern layer, okay. They are very strongly bound to the negative charged wall, and because of the negative charge on the wall more positive charges are also attracted towards the wall. So there is a region close to the wall where we would find net positive charge, okay, and that region is known as electrical double layer. It is known as electrical double layer, okay, and beyond this electrical double layer we would have the neutral liquid, where you will have equal number of positive and negative charges. So this immobile static layer is known as Stern layer or Helmholtz layer, and the region of the liquid close to the wall where we have net positive charge provided the surface is negative is known as diffuse layer, or it is also known as Gauss-Chapman layer, okay. Now when we apply a voltage difference between the two terminals, these positive charges as this region is rich in positive charges they tend to move towards the negative electrode, which is the cathode. So in doing so they carry the bulk of the liquid along with it, so we have a pumping action taking place from positive to negative terminal, okay. So we have a pumping action taking place. If you look at the potential variation from the wall into the bulk of the liquid, let us call this z direction, or in this case let us call it the y direction, then this is how it is going to vary. This is how the potential phi is going to vary from the wall into the bulk of the liquid. The potential right on the wall is the wall potential, which is denoted by phi wall, and the potential at the Stern layer or the immobile layer is known as zeta potential, okay. So Xi is called zeta potential, which depends on the surface as well as the liquid that is present on the surface. So this zeta potential is the potential at the Stern layer, okay. So the electric potential from the wall is reduced into the bulk, and about the length scale of lambda d it reduces to 0 into the bulk, okay, and this length scale is known as lambda d is known as Debye length, okay. So lambda d is called Debye length, which is the length scale at which the potential reduces to 0 in the bulk liquid, okay. So this is a very important parameter in the definition of electrical double layer, okay. which is called Debye length. Now if you look at the Zeta potential for different materials, as I told, it also depends on the liquid that we are talking about. For glass, the Zeta potential is varying from -88 to -66 depending on the liquid, and for PDMS it is found to vary between -110 to -68. Okay. And this Zeta potential, as you would see in subsequent lectures, you will see that this Zeta potential is a very important parameter that governs the electroosmotic flow. Okay. Now let us talk about the continuum model for the electrical double layer. So here if you look at this case, we will be considering this case. Okay. So here we talk about continuum model, of Debye layer. Okay. So here we consider a positively charged surface. So the surface is positively charged, okay, as you can see here. So it has got positive charge. So we would have a charges from the liquid, the negative charges will come and bind to the surface because the surface is positively charged, and inside the diffuse layer we would have net negative charge, okay, because the surface is positive, we would have negative charge close to the surface in the diffuse layer, and the bulk will be neutral. Okay. So this is the Stern layer, and this is the diffuse layer. Okay. And lambda d is representing a length scale where the potential vanishes to 0 from Xi potential at the Stern layer. So you can see a potential at the wall or at the Stern layer is given by Xi, and it vanishes to almost 0 at the Debye layer length scale. And if you look at the concentration of the charges, what you see here, the co-ions are suppressed near the wall. Since the wall is positively charged, the positive charges in the liquid is less at the wall and it increases to a value C0 in the bulk. Similarly, the counter ions are higher at the wall and they reduce to C0 into the bulk. Okay. So if you want to talk about the continuum model for Debye layer, we can assume the charges follow the gas law, okay, as ideal gas. We can assume the charges as ideal gas. If you do that, and so we have to consider for thermodynamic considerations, and in that case we will have to consider what is called the potential of the liquid. Okay. So the chemical potential of the liquid is what we have to consider. So we can define the chemical potential okay for thermodynamic consideration to treat charges or ions as ideal gas. So we can write the expression for the chemical potential as this. So we can write mu plus minus R is equal to mu 0 plus Boltzmann constant into temperature into ln of C plus minus R divided by C0 plus minus JD into phi R. So, this is the charge and this is the potential. Okay. This is the chemical potential in the absence of electric potential. So, chemical potential when phi r equal to 0, and so this is for a given phi r, this is the chemical potential, and this is the Boltzmann constant and this is temperature. Okay. And these are the ionic concentration, and C0 is the concentration or the ionic density at 0 electric potential. Okay. Now, if we talk about thermodynamic equilibrium, the chemical potential inside the ionic liquid has to be uniform. Okay. If it is not uniform, the charges or ions can reorganize themselves to generate energy. Okay. So, for the the thermodynamic equilibrium consideration, the chemical potential must be uniform. Okay. So, the gradient of the chemical potential must vanish. Okay. So, for thermodynamic equilibrium, the chemical potential mu r will be constant. So, the gradient of chemical potential will be 0. So, if you take gradient of the chemical potential here, what you will get is this, you will get Kb into T, Boltzmann constant temperature, gradient of ln C plus minus R divided by C0 will be equal to minus plus Jd into gradient of phi r. Okay. So, that is what we would get. Now, we have the boundary conditions that C plus minus infinity at z equal to infinity, r equal to infinity, the concentration is going to be C0, that is in the bulk of the liquid, and the phi at infinity will be 0, okay, no potential in the bulk, and phi on the surface will be zeta potential. Okay. So, if you apply these boundary conditions on this equation, what you would get is this, you will get the distribution of the ions C plus minus R is C0 into exponential minus plus Jd over Kb into T into phi r. Okay. So, this is the distribution of the ionic density. So, if you know distribution of the negative and positive ions, you can calculate the electrical charge density, can be calculated as Jd into, so this is across R, could be C plus R minus C minus R. So, this is the charge density which it can be calculated as minus 2 Jd C0 into sine of H sine hyperbolic into JD over Boltzmann constant temperature into potential. Okay. Now if you apply this Maxwell's equation that we had studied, del square phi r will be minus 1 over epsilon into electrical charge density. Okay. So if you use this equation, so we have an expression for electrical charge density which is this. So we can find del square phi r will be 2 JD into C0 over epsilon into sine hyperbolic JD over KB T into phi r. Okay. So this is what we would get. Now if we consider that the surface is flat, okay, then we are considering that the variation is going to happen only in the along a direction normal to the surface. Okay. So in that case phi can vary in a one dimension. Okay. So if you are considering a flat surface, considering planar surface, we can say that phi, let us say, is function of phi z, okay, where z is this direction here. Okay, this direction is z, this direction is z. Okay. So so you can write del square. So here you can say this is phi z and that is here is phi z. So you can substitute solve for the potential and write that phi z is going to be 4 kV into T divided by JD into tan inverse hyperbolic arc tan H of JD into zeta potential divided by 4 kBT exponential minus Z by lambda d. So this is how the potential is going to vary away from the wall in a direction normal to the wall into the liquid. Okay. Now we have introduced one parameter here, lambda d, which we call as Debye length. Okay. And here lambda d is defined as, so here lambda d is defined as epsilon into Boltzmann constant in temperature divided by 2 into charge square into C0, that is the concentration in the ionic concentration or ionic density in the bulk. So that is how the Debye length is determined. So there is a square root of that. So this is this represents the length scale from wall where the potential is reduced to 0. Okay. So this is reduced to 0, and if you take an order of magnitude, you can take an example. So the concentration of the charge ionic density, let us say about 1 mole per meter cube. Okay. And let us say we consider water, so epsilon is 78 times epsilon 0 the permittivity, and let us say charge is 1 unit, then and temperature is the room temperature which is 298 Kelvin, okay, consider 1 coulomb. Then we can find lambda d is about 10 nanometer, okay. So that is an estimation of how thick the Debye layer is. So Debye layer is of the order of 10 nanometer, okay. So next we move on and talk about the Debye-Huckel approximation. So we talk about Debye-Huckel approximation. So the approximation is based on the fact that the electrical energy is less as compared to the thermal energy, okay. So that is the approximation on which the Debye-Huckel approximation is based on. So we can say that JD into Ji is less than, so this is energy, right, charge into voltage is less than the thermal energy is Boltzmann constant into temperature. Now if you impose this condition, on this equation here, okay, on this equation there, then what we see here is sin h of some term, right, and we know that sin h u will be equal to u when u is small, okay. So if you impose this condition coming from the Debye-Huckel approximation on this equation here, then we can simplify the equation for the potential. We can write that del square phi r will be equal to 2 JD square C0 divided by epsilon into phi r divided by kBT, okay. So this is what we get, okay, JD over kBT into phi r becomes u and the sign hyperbolic goes out. So 2 JD C0 over epsilon, right. So we have this JD here, so that makes it JD square into C0 over epsilon into phi r over kBT. So we can write this as, here if you look at the expression for lambda d, okay, so you can lambda d square 1 over lambda d square will be this, right. So this is nothing but 1 over lambda d square. So you can write this as 1 over lambda d square into phi r, right. So we have the equation del square phi r is 1 over lambda d square into phi r. Now if you have a planar surface, for a planar surface you can write del square phi z will be equal to 1 over lambda d square into phi z. Now to solve this equation we can apply the boundary conditions. The boundary conditions are the potential when z equal to infinity will be 0, so that is in the bulk liquid, and the potential at z equal to 0 will be the Zeta potential. So if you apply that to this equation, what we would see is we get an expression for the potential, which is zeta into exponential minus z over lambda d. So this shows how the potential varies from the wall into the bulk. So we see that the potential decreases exponentially from the surface into the bulk, and that is what we see it here. Okay, if you look at what we have represented pictorially here, we see that the phi is reducing exponentially into the bulk liquid. Okay, right. So see that phi z decreases exponentially into the bulk liquid. Okay. Now you can find the charge density. Charge density can be found. So electrical charge density will be equal to minus epsilon del square phi z over del z square, right. So this is nothing but this equation that we just talked about, this equation. Okay. So we can find the charge density, knowing the charge density we can find what is the concentration of the ion. The ionic density is C0 into exponential 1 minus plus Jd over kBt into phi r. Okay. So this is the expression for the general expression how we can know what is the ionic density knowing the potential distribution. Okay. So we can write in this one dimensional case C plus minus Z will be equal to C0 into 1 minus plus Jd plus kBt, and we have an expression for phi z. Okay, we have an expression for phi z here. So say exponential minus z over lambda d. Okay. So what we see here is if you look at the ionic density distribution, it says that the coions, okay, if the wall is negatively charged, the negative charge in the bulk in the liquid are suppressed close to the wall, and it can increase into the bulk, whereas the counter ions are more close to the wall and they reduce into the bulk of the liquid. And so this is what we observe here. Okay. So the co-ions are suppressed near the wall and the counter ions are more near the wall. The co-ions increase into the bulk and the counter ions are maximum at the wall and decrease into the bulk, and they reach a value which is the value when the potential is 0, which is into the bulk of the liquid. Okay. So this is what we observe from this equation. What we see here is co-ions are suppressed near surface. Okay. You can say that if you look at the sign here and there, you can predict this. Co-ions are suppressed near the surface and the counter ions are enhanced near the surface. Okay. So, if you have a wall which is negatively charged, then if you look at the charge distribution inside the liquid, there will be more positive charges close to the wall and it is going to reduce into the bulk, and there will be less negative charge close to the wall and it is going to increase into the bulk of the liquid. Okay. So, with that next let us talk about the Debye layer capacitance. So, as we understand, the Debye layer stores some charges, and because of which there is capacitance that develops across the Debye layer, and we try to see what is the value of this capacitance. Okay. So, let us talk about Debye layer capacitance. So, let us first. So, this is shown pictorially here. So, we talk about Debye layer capacitance. Okay. So, you can see here there are two plates, one plate has positive zeta potential and the second plate has the negative zeta potential, and this is how the potential is going to vary from plate 1 to plate 2, this line. Okay. So, this is how the potential is going to vary between the two walls. Okay. Now you have a Debye layer close to both these walls, this is specified by lambda d. Okay. So, what is happening is you have a capacitor configuration here, okay, because it is storing charge, and you have another capacitor here, and then inside the bulk you have some kind of a resistor. So, if you look at the electrical equivalent of what is happening between the plate 1 to plate 2, this is how you can represent. So, you have capacitor here, okay, and then you have another capacitor close to wall 2 here, and then the bulk of the liquid can be considered as a resistor element. Okay. So, you can calculate the charge per unit area at each of these walls. So, you can calculate charge per unit area A, and so this is how you would calculate the charge Q liquid will be integration 0 to infinity the charge density, variation of the charge density along Z into dz. Okay. So, we can 0 to infinity, we have an expression for the charge density which is given by minus epsilon xi over lambda d square into exponential minus z over lambda d, okay, into dz. Okay. So, this charge density expression we have already derived it here, right. So, this is the positive and negative ions, so you can find out what is going to be the charge density from this what we have written here from here. Okay. So, you can find the electrical charge density which will come out to be this. Okay. So, this is the electrical charge density. Now, if you integrate, what you get is minus epsilon divided by lambda d into xi. Okay. So you are saying charge is given by this ratio here into the zeta potential, okay. So this acts as a potential, this is a zeta potential. So you can write capacitance, okay, Q equal to the charge equal to capacitance into potential. So capacitance you can write C is epsilon over lambda d, okay. Now if you use lambda d as about 10 nanometer and it is liquid, so epsilon is about 78 times epsilon naught, which is for the free space, then you can get an expression for get a value for the capacitance across the Debye layer, which is of the order of 0.072 Faraday per meter square. So this is the charge we are calculating per unit area of this plate, okay, this plate, okay, per unit area of one of these plates. Now we have a liquid which is having finite electrical conductivity, okay. So the liquid that is present between these two plates has got finite electrical conductivity, so you know its resistivity also, which is inverse of the electrical conductivity. So from there we can say the resistance of the liquid will be the thickness divided by electrical. So resistance is SL over A, right, this is resistivity into length divided by the area of cross section. So 1 over rho is the resistivity into H divided by area. So this is the resistance, okay. So this is the resistance of the liquid, okay, and the capacitance, so we have two capacitors here, okay, they are connected in series, okay. So we can find the equivalent capacitance. So equivalent capacitance will be epsilon A over 2 lambda d, okay. So we can define a characteristic time constants, we can define a characteristic time constant which is tau RC is equal to resistance into capacitance, okay. So which is equal to H over electrical conductivity into area, that is R, C is epsilon A over lambda d, okay, 2 lambda d, right. So you can write this as epsilon by 2 into electrical conductivity into H over lambda d. So this is the expression for the time constant. So this is the time constant for this system where we have two capacitors and one resistors in series. So if we say lambda d is of the order of 10 nanometer and the height h is of the order of 100 micron, sorry, the h that we define for the resistance is the resistance of the channel, not this is lambda d, okay, H is here. So this is H, this is basically the gap between the channel because lambda d is very small. So this is shown here, this is H. So that is the resistance of the liquid. So H is about 100 micron, and the relative permittivity is assuming is water, so it is about 78, and electrical conductivity is about 10 to the power minus 3 Siemens per meter. So from there we can find tau RC is of the order of 3.6 millisecond, and we can find the angular frequency also 2 pi divided by tau RC, which is about 1.7 into 10 to the power 3 radian per second. Okay. So from this characteristic time constant, what we understand that if you have a process, okay, let us say you are trying to use AC electroosmosis, if the frequency of the applied voltage is such that the the time available for the Debye layer to form is less than 3.6 millisecond, then the Debye layer will not be able to form. Okay. So you need at least 3.6 millisecond for the Debye layer to form to make the electroosmotic action to happen. Okay. If you use AC electroosmosis and the frequency is sufficiently high that the time available is less than 3.6 millisecond, then it will not work, the electroosmotic pumping will not work. Okay. Considering this example for the height and lambda d and the liquid that we consider. Okay. So here what we understood is that process slower than 3.6 millisecond, you have time available for Debye layer. Okay. And if the time is less than 3.6 millisecond, Debye layer is not formed. Okay. So that is an important conclusion we learn from by talking about the Debye layer capacitance. Okay. So let us stop here.